Right. So our current assignment and unit of work deals with linked lists. All right. And linked lists, rather than having a big allocated block of memory throughout your code, we instead create nodes. Nodes contain they contain two things. The first is that they contain the item, right? They store the memory location of the item you want to store, right? Just like an array list would store the memory location of the item you want to store in the array list. But they also happen to store the memory location of the next node in the linked list. The effect is something like a scavenger hunt through your memory, right? Where each node tells you where to find the next item in the list, right? So, and typically, and if I wasn't drawing them quickly in the slides, and I finally figured out the best way to draw these things in the pre-recorded videos, then I'd be drawing them like this to be exact, where basically I show that the next variable has a what's being stored in next. Oh, it's the location of the next node in the list, right? Pointing to that. But generally, what I do is I simplify this. I simplify this diagram. I take this diagram and I simplify it just to be this, right? Where the one node is represented by a square and it's pointing to the next node using an arrow, right? And this is actually pretty typical for diagrams of data structures, where we will just we'll represent nodes, which we'll be seeing a lot of, and we represent the node by a square or a circle, and then their connections with an arrow, right? And the name of the connection differs from one data structure to another. Like in here, where we're going to be using next, in another data structure, once we get the trees, rather than being called next and previous, the pointers are going to be called left and right, because they're going to be left and right, rather than that's what they'll represent. But a name is just a name, but names give things meaning, and that means we're also better able to understand it. All right. So what happens with a singly linked list is this linked list I drew over here is singly linked, right? And now that I've got something more abstract, I can make the square smaller so I can actually fit stuff in, right? Right. So one node points to the next node, which points to the next node, which points to the next node. And the last node in the list, we can either represent, it just depends on your personal preference. You can have an arrow that points to nothing to indicate that it points to null. You can have an item that points to an X to represent nothing, right? That points to null. Or you can do what I do and be lazy and not draw anything at all, right? To say that there is no next pointer, it doesn't point to anything, right? Right, and I use the term pointer a whole lot, even though that's not correct. Technically, it's the references, but since I'm using arrows, the incentive is it's just too hard to break, saying they point to this or something like that, right? So now the first node in the list we call the head, right? Just because it's the head of the list, and we typically call the bottom of the list if we keep track of it. We don't need to keep track of the last node in the list, as you'll see. But if we keep track of it, I call it the tail. Okay? The head and the tail. Again, this is singly linked, meaning that basically each node keeps track of only one other node, the one behind it. As we see in doubly linked lists, they also would keep track of the guy behind them using these. This is next. This is previous, which I abbreviate prev. So doubly linked list basically means we have 2 pointers, but I'll just stick for singly linked for right now, but now you know what a doubly linked is. And fortunately, they operate pretty much the same way. The advantage of having a doubly linked list is that you can go backwards if you want to through the list. Singly linked list, you can only go forward through the list, right? And these things operate like any other list. And what I show you guys in the video is that there's only like 5 scenarios you have to concern yourself with for add and remove. 3 if you're not keeping track of the tail. So I start out with being simple and not keeping track of the tail, so that just gives us 3 scenarios for how to add an item to the list. To add an item to a linked list, it's fairly straightforward. If it's out of bounds, don't add it. That's scenario 1. Scenario 2, you're adding a new head to the list. And what we do, as I show you in the video and show you how to do the code for that, we just create the new node, we attach it to the linked list, and we make this guy the new head of the list. And then the third scenario is we'll just adding anywhere else, which is pretty straightforward. We get, say I wanted to add, say this is index 0, 1, 2, 3, 4, right? Those are our indices. Say I wanted to add a new item to index 3. What I do is I find index 2, the node before I want to add, so I label him before. I create my node. I attach my guy to the node after before. And I just move the pointer for before over this guy. Again, I go over this in much more detail in the video. And now I have to go ahead and I'm just going to manually over here just renumber these guys just simply to up, right? Because this guy will now be 3 because he's at index 3 now, right? So we just can insert an item anywhere we want to, essentially by just inserting a new basically thing in our scavenger hunt and updating the directions accordingly, right? Notice that this node didn't really have to know anything about what was going on, right? Because he doesn't care about how people get to him. All he cares about is who comes after him, right? In a AA linked list, he'd have to do some adjusting on his own, but it's fairly straightforward to do that. Now, linked lists are actually pretty useful because the nice thing about adding to a linked list is that it's a constant time operation if you're adding to the front or to the end, right? Why? Because, well, to add to the front of the linked list, all I have to do is just draw a box, point an arrow, and I'm done. Or in terms of actually writing code, create a node, attach the .next variable, and then update head to be the new head of the list, and I am done, right? It doesn't matter how big the list is. Similarly, for adding to the tail, well, that assumes that I'm keeping track of the tail with the tail variable, and similar, I just simply draw a box, create an arrow. It doesn't matter how big that. I don't have to shift anything around like I do in a array list. Disadvantage. Well, if I'm going to be going through this linked list, basically if I want to get to index 4, I actually literally have to walk myself to index 4 because I don't know what memory location that is. I have to go and say, okay, I'm at index 0, I want to get index 4, so I'm going to move forward 1, I'm going to move forward 2, move forward to 3, move forward to 4, so I can move forward 4 times, so I'm at index 4, so I found the item. But getting to a specific index, unless it's one you've saved, which is something you can do, is an O of n operation. The other advantage to a linked list, which doesn't necessarily which unfortunately doesn't really come up, and I was trying to write an assignment that really showed this, but I didn't get the chance to, just because between the videos and stuff, so I'm using my older assignment, but I think I'm going to post this newer one as like an extra credit or an alternate or something. The great thing about linked list is that you can just split them apart and move pieces around of a linked list very easily, that in a way you can't do for array lists, because you can basically say, oh, I want to take this chunk and move it to the end of the list. Okay, that's pretty easy. I just simply separate this connection, keep track of this node, make this guy the new head, and point this guy over to here, right? You just simply maneuver those pointers, and you can basically slice these things up a heck of a lot easier than you can other data structures. What I may have just described may have sounded a bit hard, but computationally it's really easy for us to manipulate these data structures because it's just a matter of just drawing arrows around, essentially, on a whiteboard. But, yes?
So what you just did 2 just become your new head?
Yes, it did. Okay. 2 just became the new head of the list. The big thing that we have to keep track of when we're dealing with these operations is that whenever the head or the tail is going to change, we have to update the head and tail. We just have to remember to do that. And that's a lot of times what I see the error in programming. Now, your assignment for these upcoming weeks before the exam is you are going to be dealing with a special type of linked list, but not an esoteric type of linked list. Like BOGO sort is a completely made-up algorithm that only exists in an algorithms class. These types of linked lists actually do exist, and they're what we call circular linked lists, and they are pretty easy to understand, right? The tail of the list doesn't point to anything in a regular linked list. In a circular linked list, the tail goes ahead and it points to the head, so it becomes a ring, right? So you can basically the linked list wraps around, and this is useful if you are simulating a ring, or something that you need to loop around with, right? So that becomes very easy. That comes in handy, especially since for the Josephus problem, what we're going to be doing is solving for a ring. So that's the brief overview of a linked list. I provide some skeleton code for you. And the nice thing is that there are 5 scenarios for add and for adding with a tail, and I'm assuming that you're going to want a tail, okay? You're going to have to probably add your own inner node class, which you can see how to do in the video. That's making a private static class, right? So it's not really that hard. It's like the first video that I show you how to do on a linked list. But that's okay. So let's go ahead and go over the homework itself. Okay. Okay, teaching. Data structures, assignments. So the extra credit I'm planning on working on is an encryption algorithm. So let's see, what did I just hand you? So I handed you this code, right? Keep track of a head and tail variable, right? I give you a head and tail and a size. I remind you to keep track of the size, right? And I did not make you, oh, no, I made you your private static class node E already, so you don't have to add that. That's just basically what it is an inner class. It's a class only used by the class that it's inside of. This is useful because you will probably have the code, right, for my singly linked list, the code for my doubly linked list, and your own code, and they all have their own nodes, right? So the nice thing is that by having this here, by having a private static node class, it means that basically that those nodes aren't going to get mixed up with each other, right? They use one node, the other one uses a different type of node, and this one uses this node, okay? The other thing is that I wrote this thing called an iterator, which iterates through your list. You'll want to use it to solve the actual Josephus problem when we get into it, but notice I say provide code, read the comments to figure out how it works. You should not have to change this. Change it at your own risk. Right? And it's not static because it needs the rest of the class it's inside to survive. It can't just, it relies on calling the list methods. It will call some of your methods that you write. And your objective is basically you just have to do the add and remove methods, and I list the cases for you guys so that it becomes a bit easier for you, right? So it's fairly direct. I've streamlined it over the years to help make it an easier assignment, so, but it is still a bit tricky. So what is the Josephus problem that I keep talking about? Let's see. Here we go. So the Josephus problem is a famous mathematics problem. You can look it up on Wikipedia. Now, we could solve it mathematically, but the equation for solving it is hideous. It is an abomination unto the Lord, so to speak. But it is, but on the other hand, simulating the process of the Josephus problem is fairly straightforward. So the Josephus problem is named after Titus Flavius Josephus, who lived from 37 to 100, so pretty long ago. He was a high priest of the Jewish religion of the time, and he participated in a Jewish uprising against the Romans, who were the current, owners of that area of the Middle East at the time. So this was a revolt against the Romans, and if you know about history, then you know that revolts against Rome all end exactly the same, with Rome being the winner and everybody else losing out. Eventually, they were surrounded. The last vestiges of the forces were basically surrounded in a cave during the siege, and Josephus had become a war band leader at the time, and they decided that it would rather be better to die than to live on as a Roman slave. Okay. So what they did is that they cast lots, essentially, basically saying that we'll all cast lots, and then whoever draws that lot, they die, and then once we get down to 2 people, they'll kill each other, right? Rather, we should all commit mass suicide rather than get conquered by the Romans and be enslaved. Josephus got lucky, and him and one other soldier were there at the end. They looked at each other and they pretty much went, "Yeah, this was a terrible idea. Let's go be slaves instead." So he was a slave, and he gained the mysterious power of prophecy by prophesying that that the person he became a slave of would become a great general. Spoiler alert: the guy became a great general, and so that helped him out there. So anyway, he then became what makes him important is that he was a historian of that era, from 37 to 100. So he basically gave a good amount of insight into how early Christianity developed, how Judaism at that time was, right? So because this is a pretty crucial time in history. This is really, really, really early Christianity going on there, and he writes about it. So anyway, what is the Josephus problem? Well, it's the drawing. Well, the problem is, suppose you're stuck in that situation where you're basically in a circle with a bunch of soldiers who are all getting removed from the circle, right? All drawing lots, right? The question is, where do I want to be so I'm going to not die? Who is going to be the last one surviving, right? So that's the Josephus question. And we don't know how the soldiers drew lots, but we suppose it worked like this. Suppose you have a bunch of soldiers just standing around a circle, right? Something like this, right? So, and I'm going to use 1, 2, 3, 4 rather than starting from 0. Just so 1, 2, 3, 4, 5, right? So we've got our guys standing in the circle, and they are going to basically remove every second guy from the circle, okay? So 1, 2, so we remove this guy. 1, 2, we remove this guy. 1, and we go around the circle again. 2, we remove number 1. 1, 2, so we remove number 5. So 3 is the safe spot to be in, right? So the Josephus problem says, for a circle of size n and a count of size k, right? Here the count was 2 because I was going every other soldier. If the count was 3, it would look something like this: 1, 2, 3, 4, 5. 1, 2, 3, remove. 1, 2, 3, remove. 1, 2, 3, remove. 1, 2, 3, remove. So 4 would be the safe spot at the time, right? So given a circle of size n and a count of size k, who's going to win? Okay, who's going to be the last person standing? Okay. I give a write-up over here about how you use a circular linked list to do this, and how the iterator works, and then I have some examples of how this output should work. I also provided you, very helpfully, I think, just so you can test your code, I gave you a toString method, okay? So this is I guarantee you this is working. So if you try to print your list and you get an error or a null pointer exception, something's wrong with your code. I guarantee you that the code I give to you will work, okay? So you can use the string builder to test this. Now, what is the suggested way to strategize this, to go through this? Well, get node, you should probably write first. Spoiler, it's probably going to be this. It will probably work the same as the get node in the singly linked list and the doubly linked list. So you should probably check that out. So that's kind of a freebie. This one we'll call this one, right? So simply swap that to true. That's another freebie. So you only have 2 methods to write, which is add and remove. And I give you the cases for doing that, right? And they're the same cases that I go over in the doubly linked list video, right? So, but there's a lot of just little things that you just need to keep mind of because it is a circular linked list, okay? So, and then I give you a main method and I tell you what to do. The first thing you're going to want to test is adding your nodes, right, and printing out all the cases for addition, just to make sure it works. And then you're going to write remove, test out all its conditions, and then figure out how you're going to use the iterator to move around and remove all the nodes to make it very easy for you. Because beyond this point, it should take about 4 lines of code to solve the problem. So to actually solve the Josephus problem is about 4 lines of code, 4 to 5 lines. Okay, so that's it. You guys can go ahead and get started. I will not be here on Wednesday, but I will. And I'm not also going to be here for the Tuesday night lecture. But to make it up, I'm going to try to make it to your labs. So, it was at the very first lab just to make sure that, very first lab last week just to make sure that the timed lab did not completely blow up.